Hello and welcome to another video. In this video, we're going to be working on amount of time for a binary tree to be infected. And in the problem, you're given the root of a binary tree with unique values and an integer start. And at minute 0, infection starts from start. And at each minute, the node becomes infected if it's uninfected and it's adjacent to an infected node. Return the number of minutes for the entire tree to be infected. So for this, it's going to be 4 because these nodes are infected at 1. This is 2, 3, and 4. So it's basically just how long does it take for the last node to get infected is your answer, really. And so here, this is 4, and this is 0 because the whole tree is infected right away. So, and there are a lot of nodes here, so it's 10 to the 5th node, so you're going to want like something linear here. And so there's kind of two ways to do this, and I think the more intuitive strategy is to build a graph out of this and then to just BFS this graph. So we're actually going to take this picture here, this example 1, and this is the one we're going to use. So essentially, what we need to do is we need to, instead of having a tree, because we can't traverse like up, right? Like if this is our infected node, we can't traverse up. So instead of this tree, we're just going to build a graph. And it's pretty straightforward. You just do a normal DFS traversal. And for every single node and its children, you just build a path from the node to the child and from the child to the node. So once you do this, you're going to have a graph of 1 that goes to 3 and 5. And then we'll make this in order. 2 will go to 4. 3 will go to 1, 6, and 10. And let's see, 4 will go to 2, 5, and 9. 5, let's actually draw it over here, will go to 1 and 4. And 6 will go to 3. And we have 9 and 10 left, so 9 will go to 4. And 10 will go to 3. So once you have this, you can just, now your problem is basically, I have a graph instead of a tree. So given some starting key, like this key, how long does it take to visit every other key? And because you have a tree, every node is going to be connected, right? In a tree, every node is connected. So you just do like a straightforward BFS from 3. And once you visited everything, then you're done. And so we can actually move this tree up and show what this is, or move it down maybe, and show what this traversal is going to look like. So this is pretty straightforward BFS. In a straightforward BFS, you're just going to start with a queue with one node. We'll start with 3. And we're going to have a visited set. So as soon as your thing can go into the queue, you can put it into the visited set. We'll call this like V or something, because once something is in the queue, like in the normal graph traversal, if the edges are unweighted, that's going to be the fastest way to get there, right? So if I go from 3 to 1, there is no other way to 1 that's faster than that, right? So any graph that has this equal length edges, just the BFS is guaranteed to get you there faster. So, or fastest. So once you get to a node once, if you get there again, it's going to be slower, so we don't need to put it in again. So we put 3 in our visited set, and then basically for every node, and then the other thing we need to also record is, you can do this in a few ways. You can either have tuples of a node and the number of moves it took there, but in this case, there's actually another way to do it. And so the other way to do it is you just have a global variable. So we'll call this like moves, set it equal to 0. And then basically you just, instead of going one node at a time, you just run through each iteration of the items in here. So each time you take all the items in here currently, you put in all the children, and then if there's something left, you increment the moves. So let's kind of show how this will go. So for 3, we will go through all of its children. So it's 1, 6, and 10. So we're going to take out 3, put in all of its children, 1, 6, and 10. And then we will increment the moves because there are nodes in here. So this will be 1. And we can also add 1, 6, and 10 to visited because, like I said, they're in the queue already. So we have 1 move, and this is the same as a picture as 1 move to all of these. Then we go back. And basically what we want to do now is we only want to iterate through all of these, add all of their children in, and then stop when these are done. So we'll make like a little divider. So we just want to go through these, and I'll show you how to do that in the code. So for 1, it goes to 3 and 5. We've already visited 3, so we'll add 5. So 5, add 5 to our visited set. For 6, it goes to 3. We've already visited that. 10 goes 3, we've already visited that. So these are all done. And now our queue is only 5. And since this is non-empty, we add another move. And this is the same as going over here. So for 5, we have 1 and 4. We've already visited 1, so it's just 4. Increment the moves. And here it is. So this is the same as this. Then for 4, it has 2, 5, and 9. Oh yeah, we forgot to add 4 in here. And what else did we forget? I think we should have all of the rest. Let's see, there should be 6 nodes. Yeah. Okay, so for 4, we have 2, 5, and 9. 5's already visited, so we just add 2 and 9. So we get rid of the 4, we pop it, add 2 and 9. And since it's not empty, we increment the moves again. So that's the same as going here. Now for these two, there's nothing in here that we haven't visited yet, right? It's just 4 and 4, and we've already visited 4. So we would have an empty queue, and we would basically just return 4 here. And so that's kind of how you do it. First, you build a graph, and then you just BFS from whatever your start node is until you visit everything else. And the way you know you visit everything else, because it's all connected, is just when your BFS is empty. And for each iteration of the BFS, you take all the nodes, you add in all the children, and if there are moves left, or if there are nodes left, you want to increment the moves. You want to increment the moves after you add the children, because for something like this, your BFS would just have like 1 in here. And then basically what would happen is it would have no children. So you would have an empty BFS afterwards, and then you check like, okay, no children. So moves was 0 to begin with, so I'm never going to increment it. So you increment after you take the current node that you're at and add the children, because that means you went from your current node to the children, right? That's like going from here to these 3 and so on. And then for every iteration from then on, you just increment. And I'll show you how to do that in the code, like I said. So yeah, we can just code it up now. So first we're going to build a graph. So we'll just have a graph. That's just going to be a default dict. And we're going to make a DFS function to traverse the tree to build a graph. So we'll just say def traverse and node. If a node has a left child, then we will make a path from the node to the left child and back. So graph node.left.val. And we're just going to use node values instead of the actual nodes themselves, because we don't need to use a node, so we can just use node values. So I'm going to add the current node and make the other addition. So we're going to say graph node.val and the left one. And then finally recurse left. And then we're going to do the exact same thing for the right side. So right, probably just do this. Right. Okay. So we have to call it. And so now we're going to have this graph where every node will be connected to all of its like nodes that are next to it. So now we just have to do the BFS part. So we'll have a visited set. We'll put in the start node, and we'll have a BFS. That will be a deck that will have the start node. And we'll have a result equals 0. And while the BFS actually has stuff, so the way you can go through all the current nodes in the queue, let's say you have like 1, 2, 3. If you want to just go through these 3 nodes and add a bunch of children, but you want to stop after 3, you can use a for range loop. So you can say like this. And basically this for range loop will take a snapshot of the length of the BFS right now, and it will iterate that amount of time, even if you keep adding more things later on. So this is pretty useful. So we're just going to say node equals BFS.pop left and for child in graph node. If we haven't visited yet, then let's add it to the visited set. And let's append it to the BFS. And so after this like snapshot is done, like for example, let's say you have 3 nodes and these 3 nodes have children 4, 5, 6. What's going to happen is these 3 nodes will get popped. That means this loop iterated 3 times. The children will be added like as they're being added, and now you'll have this for the next iteration of the BFS. And now we want to say if the BFS actually still has elements in it. So if BFS let's increment the result. And finally, at the end, let's return the result. So run this, submit. And it's pretty good. So pretty efficient. So let's talk about the time and space for this one. So essentially, this traversal is O of n. This BFS is also O of n. We're not like repeatedly visiting nodes, so we'll visit every node once. And for space, the traversal is O of n, as always, in stack space. The visited set is O of n, and BFS is O of n. So that's O of n. And I think this is like the most intuitive way to do it. So I think that's going to be all for this problem. And then one small thing, so I started coding in Java, so I might start doing problems in Java, and let me know if you guys would rather see Java or Python, or if you don't have a preference. And yeah, if you did like this video, and if you found it helpful, then please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.